As everybody knows, Christmas is all about tradition, and so here's our keenly awaited annual tutorial demonstrating how to use RailClone to model an unconventional Christmas tree. This year we'll demonstrate how to stack any model, either your own or a stock object, into a cone shape to create an eye-catching tree from nearly any geometry. Along the way though, you'll learn some core RailClone skills, pick up some tips for using the A2S array's Y mode settings, and see the power of using simple expressions. So let's get started. First, create a new circular spline to define the footprint of your tree. Then create a new RailClone object and open the style editor. Add a new A2S generator. This is going to be used to create 2D array, and it has the ability to control the X and the Y sizes with either splines or numeric measurements. In this example, we'll use the circular spline for the X-axis, but we'll use a value for the Y-axis. So to add the spline, create a new spline node and use it to select the circular spline from the scene. Wire the spline node to the generator's X-spline input. To control the Y size, you can use the parameter in the generator's properties, but to make it easier to edit, we'll export it to the Modify panel. To do this, right-click on the generator and select Export Parameters. Select Y size and click OK. To add a parameter to the Modify panel, we add a numeric node. Name it Radius, change the type to Scene Units, and wire it to the generator's Y size input. So we can't currently see the results yet because we haven't added any geometry. So create a new segment node and pick an object from the scene. For this example, we'll use the venerable 3ds Max teapot. Wire the segment to the generator's default input. We don't want to cut this object, so disable Slice in the segment's properties. You may also want to disable Bend to prevent the geometry from being deformed to follow the curvature of the spline. You can now edit the radius value and the array will expand towards the centre of the spline. As you can see, the number of teapots in every row is identical. This means that as they get close to the centre, they've got to overlap. There is a little known mode in RailClone that allows the segment count of each row in a 2D array to be calculated independently. To enable it, you simply go to the generator's properties and change General Y mode to Free. And you can see there are also still sliced segments at the end of the array. This is because the teapots don't fit exactly into the circumference. So to fix this, change the generator's properties rules default mode to adaptive. This will subtly scale the geometry to ensure whole segments fit in the available space. To calculate the spacing of adjacent segments, RailClone uses the object bounding box. The side used for the calculation depends on the alignment settings. If we turn on box display mode, we can see in this example that the outer edge is being used, and this explains the overlap. If the outer edge is touching, the inner edges will overlap. So to fix this, we can change the segment's alignment by adding a transform node between the segment and the generator. Enable alignment override and change Y to top. The segments are now aligned to the inner edge and they no longer intersect. So now we have the basic layout. The next step is to move each row up on the Z-axis to form a kind of conical shape. For this, we'll use an expression. And if that word alarms you, don't worry. There's a misconception that expressions in RailClone are programming. They're not. They're just a simple way of doing some maths, and they give you access to a few values that aren't available elsewhere. First of all, you need to export a parameter that you want to control with an expression. This is no different from exporting the Y size of the array we looked at earlier in this tutorial. This time we're going to export the fixed Z translation from the transform node. Next, create a new arithmetic node and wire it to the Z fixed translation input. Go to the arithmetic node settings and change the operation to expression. To create an expression, we open the editor by clicking Edit Expression. The expressions editor is divided into three parts. On the left hand side you have two tabs. Attributes show you all of the values that you can use in your equations. There's no need to remember these because they're all listed for you. The other tab shows you the mathematical functions that you can use to go beyond simple operators like plus, minus, divide, multiply, etc. Again, these are listed so you don't need to remember them. To see more information about an attribute or a function, just select it from the list and the information is displayed in the bottom right panel. Here you'll find a description and an indication of how it can be used. Above this you have the text editor, which is where you write the expressions themselves. For simple expressions there are 3 parts you need to include. First of all, you should type return to tell RailClone to output the results of the following expression. Secondly, you enter your expression. It could be something as simple as 1 + 1. Finally, each line needs to be terminated with a semicolon. So a typical expression might read return 1 + 1 semicolon, and the output from this would be of course 2. But let's try a real world example. We want to increase the Z offset by a set distance for each row in our array. But first of all, let's add that all important return command. Next, we need to find a counter that increases for each row that we can use to multiply a value. If we search through the list of attributes on the left hand side, you'll find there's one called segment Y counter, which sounds promising. If you click on it, the description reads segments index along the Y path. Perfect. To add the attribute to the equation, you don't even need to type, just double click to add it automatically. Now we need to multiply this by the distance we want each row to be offset. In order for segments to stack, this should be the height of the geometry. We could enter a value manually here, but then we'd need to change it if we swap or resize the segment. Instead, it's better to extract the dimensions automatically. You can do this by right-clicking on any node and selecting Export Attribute. In this case, we want to export the Z size from the Transform node. And then wire this to the arithmetic node's first input. So we have an input, but how do we reference it in the expression? Well, to do that, you just enter input followed by the number of the input starting from 1 at the top. So in this case, you would add multiplied by input 1 to the expression, giving you a full readout of return segment Y counter multiplied by input 1. And then finally, don't forget to add that semicolon. So now if you click evaluate, you should see a stepping effect. This is looking great, but you'll notice that the first row is also stepped, so the array is hovering above the ground. This is because the first row is being translated, and really we only want the effect to start from row 2. So you can achieve this very easily by just subtracting 1 from the Y counter value, which of course starts at 1. So the full expression would read return open brackets segment Y counter -1 close brackets multiplied by input 1 semicolon. And here the brackets are just used to control the order of the mathematical operations. And that's the stepping effect complete. To finish off this part of the tutorial, we just need to change the segments so they're able to overlap and stack on top of one another. And to do that, we'll use the transform operator's bottom padding value. If you enable padding and reduce this value, you'll see that the rows start to overlap and the tree gets taller too. We can make this easier to edit by exporting the value and wiring it to a new numeric node, which we'll call overlap. Don't forget to make sure you set the type to scene units, and then this value, like the radius, can now be controlled from the modify panel. As an extra option, you can also add shelves between rows. This would work well for objects like the teapot or wine bottles that don't necessarily stack very safely. Here's how this works. So you'd select the generator, segment and transform nodes and duplicate them using copy and paste. Disable and disconnect any padding inputs, we don't need them for this part of the graph. In the copied segment node, pick some geometry for a shelf. Make sure you re-enable bend if you turned it off, or the geometry won't deform around the spline. In order for the same number of shelves as there are objects, it should be exactly the same size on the y-axis as the teapot. However, we can tell RailClone what size to use for a segment without it actually affecting the geometry. In that way, the shelf can be deeper than the teapot, but all of the calculations that determine spacing will assume that they're the same size. So to achieve that, in the new transform node, enable fixed size. Then uncheck scale segment, and this will stop the geometry from being affected by this new size. Enable the Y size attribute from the teapot's transform node. Export the fixed size Y parameter from the shelf's transform node and connect it to the Y size attribute exported in the previous step. Next, we'll align the outside of the shelf to the outside of the teapots. To do this, first change the Y alignment for the shelf to bottom. Now the outer edge of the shelf is aligned to the spline, and all we need to do is move it back along the y-axis, the depth of the teapot. This might seem like an odd way of doing things, but it allows us to have a shelf that is deeper than the teapots and everything's still aligned automatically. Right click on the teapot segment and export the Y size attribute. Notice that this is not the same as the Y size attribute exported from the transform node. The segment Y size attribute is the width of the geometry. The Y size attribute of the transform node includes the padding values that we've added or subtracted. So export the Y fixed translation property from the shelf's transform node. Add an invert value macro, which makes a positive number negative or vice versa, and wire it to the fixed translation property. Connect the segment's Y size attribute to the macro. Nearly there. All we need to do now is add the thickness of the shelf into the existing stepping expression. To do this, first export the Z size attribute of the shelf. Wire a new arithmetic node between the existing arithmetic node and the teapot's transform Z size property. Leave the mode set to addition. Wire the shelf's Z size property to the second input of the new arithmetic node. The size between each row is now the sum of the height of the teapot plus the shelf. Finally, to move the teapots to the top of the shelves, currently they're intersecting, export the teapot generator's Z offset value and wire it to the shelf segment's Z size. And we're done! So we now have a very flexible style in which all of the important values are derived automatically from the geometry. This means that you can easily change the size of the teapots and alter the depth and the thickness of the shelves, and the models will adapt. It gets even more interesting though when you swap in different geometry. We could easily change our teapots for pianos, for example, and the styles update automatically. Don't want the shelves between them? That's no worries, just clear them in the segment settings and the geometry is removed and the array closes up to compensate. You can even add multiple segments. In this example, several present models have been added simply by wiring segments to a random node connected to the transform operator. The rest of the graph is exactly the same as the tutorial. The same is true of the tree made of wine bottles. They're added to a randomized node, and in this example, the shelf is added as well. This is the final tutorial of 2018, and we'd like to take the opportunity to thank you for watching. We hope you'll stay tuned to plenty more episodes in the new year.